The first title to start with is equilibrium. What is equilibrium and how can we get it? In order to answer these questions, let's examine the following system. Here we have an elastic spring fixed at one end, and the other end holds an object. As you can see, they are moving downward, then upward, and then downward, and so on. And we can explain this simply by the fact that there must be some forces acting on them so they move. However, after a specific period of time, we're going to get a different result. Just check this one. Here, the spring is not moving and the object as well. So what is going on right here? First, let's list the forces still acting on the suspended object in particular. Right now, we will take into consideration this object only. Yes, we have the force exerted by gravity, and which is weight, and we have the force exerted by the elastic spring on the object, and which we call tension. One more time, let's describe the final state of the object. Yes, the object right now is not moving, it's at rest. Now, in this situation, we can say that the object is at equilibrium under the action of two forces. In grade 9, we will talk about two forces acting on a body, and this body can attain a state of equilibrium. Here we have another question. How can a body be at equilibrium despite the presence of some forces acting on it? In order to answer this question, we have to move to the second title, which is the condition of equilibrium. Let's take the same example, the object right now, which is at rest, and we say that if an object is in equilibrium under the action of two forces, for example, let's name them F1 with a vector, don't forget it, and F2, then these two forces must have, here is the condition, they should have the same line of action. They should act along the same line of action. They have the same magnitude, but opposite direction. In a way, if we get the sum of these forces acting on the body, the result will be zero vector. The resultant of these two forces is a zero vector. The net force is equal to zero because they will cancel each other. If we want to write a relation between these two forces, we have the vector relation, just like the one we have seen in the previous video. We're talking about force vectors. So we have F1 plus F2, we get zero vector, or F1 is equal in magnitude, but don't forget the minus to show the opposite direction for the second force, which is F2. We can also get a relation between these two forces, but this time we will talk about the magnitude relation between these two forces. And as we mentioned before, since they have the same magnitude, so we simply say that F1 without a vector is equal to F2. Right now, let's go back to the example. We have two forces, as we have mentioned before. This is the first one. Its line of action is a vertical line of action, and here is the second one. So you can see that they are acting along the same line of action. Here we have an upward direction, while for the other force we have a downward direction. And concerning the length, using the same scale, it's the same, so we're talking about equal magnitudes, and because of that the condition is satisfied. so the object is at equilibrium. Let's write the vector and magnitude relations. In order to do that, don't forget to give the name of each force. So we have the weight and tension. Starting with vector relation, we have weight plus tension is equal to 0, or we can write it also as weight is equal but opposite to tension. And the magnitude relation, just cancel the vectors, weight is equal to tension. So you have to memorize the condition because sometimes we ask about it, just give the condition of equilibrium, and sometimes we will make use of the relations that can be written in a state of equilibrium. Now it's time to make an application. First, let's read the given. Here we have a book of mass 500 grams is resting on a table as in the adjacent figure. We have to determine the magnitude of the force exerted by the table on the book. You can pause the video and try to think about it. Going back to the given, we have the mass, so we can directly think about the weight. They said that the book is at rest, so I can say that the book is in a state of equilibrium. So the condition of equilibrium is satisfied. I have to get the magnitude of a force done by the table on the book. So yes, we know the name of this force. It's the normal reaction of a support. In order to answer the question, let's move in the following order. The book is resting on the table under the action of two forces. Let's think about these two forces first and let's list them. We have the weight, and this is its name. And we have the normal reaction R. We can write R or N. And don't forget that this is the force they are asking about its magnitude. Since it's at a condition of equilibrium, so we can write the following relation. Since they act along the same line of action, they have the same magnitude but opposite direction, so the summation is equal to 0. Out of this vector relation, we can deduce the magnitude relation where the normal reaction R is equal to weight. And according to your knowledge, we know that weight is mass times gravity. So simply we can substitute by mass times gravity. Here you have to remember that the mass should be used in the SI unit. So because of that, the 500 grams is divided by 1000 to get 0.5 kilograms. Here is the gravity. We can cancel kilogram with kilogram in order to get the magnitude of the normal reaction, which is 5 Newton. The last title for this part is Equilibrium versus Interaction. Note that in grade 9, as I've said before, we're going to talk mainly about two forces acting on a body at equilibrium. In the previous video, video 1, we have seen that the forces of interaction are characterized by having the same line of action, the same magnitude, and opposite directions. Similarly, for the forces that act on a body at equilibrium, they also have the same line of action, the same magnitude, and opposite directions. In order to avoid any confusion between the forces of interaction and the forces that act on a body at equilibrium, let's look for a difference between them. Our example right here, we have a string hanging a lamp, and here is the earth. First, let's talk about forces of interaction. Let's take into consideration the interaction that happens between the string and the lamp. So we say that the string exerts a force on the lamp, S for the string and L for the lamp, and at the same time, the lamp exerts a force on the string. If you notice that these two forces of interaction are produced by different objects, and if you check the receiver, it's not the same. We actually have switching roles in this situation. Another example of interaction is happening between the lamp and the earth or the gravity. So here we have a force exerted by gravity on the lamp, and at the same time the lamp makes a force or exerts a force on the gravity. The same note concerning the receiver right here. So as a conclusion, we can say that in interaction, the forces of interaction don't act on the same body. But if we want to talk about the forces acting on a body at equilibrium, and if I say that the lamp in this case is at equilibrium, so we have a force which is exerted by the string on the lamp, and there is another force exerted at the same time on the lamp, which is the one done by gravity on the lamp. These are two forces acting on a body at equilibrium. If we check the receiver right here, we have the same receiver. So different forces exerted by different producers acting on the same body. So as a conclusion, in equilibrium, the forces act on the same body. By this, we have finished everything about equilibrium. So the second objective is covered, and which is to recognize the condition where a solid subjected mainly to two forces is at equilibrium. Now I have to thank you for your attention and see you in the next videos.